Okay, so you can hear me, right? Am I audible? Just can anyone confirm in the chat once? Okay, I hope my screen is visible, right? Okay.
Yes.
Okay. So, so this is week 6, right? So wait, let me just fix some things. Okay. Yeah. Huh. So this is week 6. So just for your reminder, week 5 we did analytics using dictionaries, right? And then functions, and we have also explored generators, right? Generator functions and how they optimize the memory usage or runtime memory usage of the program, right? Because it doesn't stores the data, it basically yields, generates the data, right? Instead of storing it. Yeah. So just for your information, let's just mark it here as well. So a a practical use case of generators are when you are reading data from hard disk. Let's say you are training a big neural network, right? And then you have a lot of data sitting in your hard disk, uh, and you don't want to read the. Let's say you are bounded by RAM, right? Let's say you are bounded at least around 16 GB. So your RAM is 16 GB and your data sheet is of 100 GB. Okay. Now you cannot load that data directly to memory. So in that case, generators are useful. Instead of, let's say, reading the whole data and basically parsing them in a loop, what you can do, you can uh, like read a set of records and then just load that in memory. Again, when I'm, let's say, I need to get another set of records, I just read the hard disk. And random generator is something else. Random generator is uh, so I don't, I'm not sure whether you attended the last class. I guess you attended, right? So generators are these yield functions, functions with yield at the end instead of return, right? So I guess you can okay, I can just go in the try. Let me just show you that. What I am saying about generators, I am referring to these type of functions. So instead of generating all the storing all the odds number, what we are doing, we are generating them and yielding them instead of storing them, right? So basically it reduces the memory usage, right? Like runtime memory usage. So one of the, like, let's say practical use cases are data loaders that we use in our, like, let's say any deep learning pipeline requires data loaders, right? So the data set is really big. You cannot load that like whole data set in memory at once. So what you do, you write a generator that would load a set of files yield to the let's say the GPU or the CPU, wherever you are training the model. And then whenever that let's say that on that particular record you have trained the model, you just like, let's say, delete it from memory and load another batch. Okay, this is a general use case of generator. So you might have heard of, or you will be hearing of this torch data loader, right? Torch data loader. Yeah, these data set loaders. These are what generators. Okay, they works as same as generators. Okay, Now, so these two we covered in the last week and did some practice questions, really simple practice questions. Record. Now this week we'll move to recursion. Now you know functions and it like two types of functions, generators and normal functions. Now another trick that any programming language can do is recursion. Okay. So I guess this week you had your material on recursion, right? So let's just like delve deeper into this and just see why, like how a function is called itself, and let's say why it is not good always. So you cannot implement any logic using recursion. Okay, there is a limitation when you should use a recursion and when you should not. So those things are important. Like whenever you are implementing a real system, like knowing which or let's say knowing which approach would be effective is very important. Okay. So let's just see. So our goal for this week's uh, like discussion is like knowing how functions call itself, right? And then also knowing why this recursion is not a good idea for all the scenarios, and some like solve some really simple practice questions that would help in your assignments too. And I'll also start with classes today. So introduction to this class in Python. Okay. So class actually it comes from C++, Java, from C++ to all the languages they have classes. C doesn't have classes. Okay. So I will tell you what like where classes are coming from and why they came into existence, right? And how they help in let's say structuring or making the code more understandable. Okay. So let's just turn on my Jupyter Notebook server. Oh, sorry. Okay. So this is for week 6. Let's just put this one as a separate tab so that we can refer to it. Okay. So now, how a function call itself. Let's see the this is a diagrammatic representation of it. So let's say I'm like getting the or printing all the let's say factors, okay, um, of a function of a let's say I am trying to compute factorial, okay. So I let's say n factorial means what 1 2 3 up, multiplication up to n, right? So this is a pictorial representation of recursion, okay. So it looks like a stack actually. So the main function that calls, and for Python you already know there is no main function. So basically the program body calls a function that is let's say 4 factorial, right? So it calls 4 into fact 3, right? Fact 4 minus 1, that's the logic. And then it basically this same structure repeats itself until the base case hits. So base case is when the functions stop calling each other, okay. So for example, see this factorial computation. So so how I can compute factorial. So without the knowledge of recursion, how would I approach the problem? Let's say I take an input from the user, right? And let's just cast it to int. Oh, sorry. So this is my number. Let's say I am trying to compute factor of 10 factorial. Okay. Now how I can approach this? So that 10 factorial basically means what? 1 times 2 times dot 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 up to 10 time 10, right? So I can use a loop anyway. So let's just forget about recursion now and implement it using a loop first. So how I can implement it? For I in range n, not n plus 1, and it starts with 1, right? Now what does it mean? It will start with 1 and go till n, right? Because the last the this extreme is non-inclusive, so it's excluded when you are looping, right? So just print them for sanity. Print I. Yes, so it's looping from 1 to 10. Okay. Now what I can do, I can just have a multiplication variable here, multi equal to 1, and see, for whenever you are summing something, the initial variable should initialize to 0, and whenever you are multiplying something, the initial variable should be initialized in 1. Okay. Now what I can do, just do multiply times equal to I. So this is basically a shorthand of multi is equal to multi times I. This is a shorthand of the same expression. Okay. This is run it. Now see, let's see what is multi. Now this is multi. Fine. Now we have we know how to implement factorial using a loop. So we can just make it a function, def uh, factorial underscore loop. So it's implemented with loop. Okay. Now let's just um, the variable is n. After the loop ended, you just return multi, right? And we already have n. Just call this function, and we have the same answer, right? Now, what factorial have a property that it basically, see this property, multi times equal to I. So this is kind of a recursive property, right? Multiplication is multiply, like this variable is getting multiplied with itself. So if I just roll the loop out, what it would look like? For the first multi times 9, and then this 9 can be represented as multi times 8, right? This 8 can be represented, no, 8 factorial actually, 8 factorial can be represented as multi times 7 factorial, something like this, right? So this is what a recursive behavior means. Okay. Now let's just, hello, wait, we just
Explain again.
yeah, I can hear you. Do you have any questions?
I just joined late.
Okay, yeah. So so just for your context, so what we are discussing is wait, oh, not this one. I'm discussing this one. So our objective would be to know how recursion works and why it is not a good idea all the time. Do some practice questions, and let's introduce yourself to classes now. So how we can structure code with classes. Okay. So till now what I have shown, you can implement anything with loop, whatever is being implemented as a recursion or self-repeating structure. Recursion means basically it repeats itself. Okay. Now that thing you can always implement using a loop. But why then recursion, right? So see, this same factorial code can be implemented with recursion like this. Factorial, and then it's do REC recursion for recursion in and for this what we will use, if n is equal to 0 or n is equal to 1. So there are two base cases, right? Because 0 factorial is also 1 factorial is also 1, right? So in those two cases I will return 1. Else what I will return, that same repeating structure, that 9 times, sorry, n times factorial of, sorry, factorial recursion of n minus 1, the previous number. So that basically means 9 times, sorry, 10 times 8 factorial, and then this 8 factorial can be represented as, sorry, 9 times 10 times 9 factorial. This 9 factorial can be represented in the next iteration is 8, 9 times 8 factorial, something like this. Okay, now let's just do a print and see whether it is like running as we expect it or not. Print n comma, sorry, let's just do this formatted string, n times factorial of what, n minus 1. This is what is happening. So you're just printing it out, and whenever it reaches the end, we'll print 1 1. Okay. See this. This is how it is unrolling. So what does it say? Okay, unsupported operand type for star, int and none type. Oh, sorry, I forgot to do a return. Sorry. Yeah. So it basically returns n time factorial of that previous one. So when I'm running it, it's computing the value something like this. So 10 times factorial of 9, and the 9 factorial is computed as 9 times factorial of 8. Similarly, all the factors until you hit the factor of 1, which returns 1. And then the stack, see this stack returns in the backward. So the stack gets generated like the downward, like 10 would call 10 would call 9 factorial, 9 factorial would call 8 factorial, something like this. And whenever it is returning, it is calling it like the values are substituted in backwards. So this 1 get replaced factorial 1, this 2 times 1 gets replaced as a factorial of 2, 2 times 3 times 1 get replaced as a factorial of 3. Okay, so this is what recursion means. Now now you can, I guess, relate to this picture, right? So the main body calls factorial of 4 factorial 4 into factorial of 3, then this factorial of 3 calls 3 times factorial of 2 until it reaches factorial of 1, and then after the base case is arrived, it just returns or substitute the last computed value with the recursion ended to the previous call, right? Okay. So this is how factorial is implemented. Now let's just try something. Wait, we just create another window so that our current window doesn't crash for some reason. Online Python compiler. Okay, now let's copy our code and see up to how much we can successfully compute factorial with what. Let's say let's go with factorial first. Now I want to compute factorial for say 10. Similarly, run. Oh, it computed the value. Let's just print the value. Yeah, so the answer, let's just do some formatting so that we understand. Format answer format. Now it gives us the answer of this with, like, successfully give us the answer of this, right? Now let's just increase the number 20. It gives me another answer. Fine, no problem. 30. Then also it gives me a good answer. Let's just go with 100. Oh, it still gives me answer, right? Let's just give it 1000. Oh, it still gives me an answer 10,000. Yeah, see, no, 1000, it breaks, right? See, code exited with error. And where it exits? It exits at factor of 203, right? So it basically calls itself 203 times, 204th time. Whenever it calling itself for the 203rd time, it gets an error. And why it gets an error? That's suspicious, right? Now let's reduce it to let's say 204. Yeah, it gives me an answer. Now if I we are just narrowing down the upper limit. Okay, so let's just give it to 205. Now let's see. Code successfully ran 6. Oh, it still runs. uh, oh no, it actually runs backward, right? So from 1000 to 204. Wait, let me just do a minus. 1000 to 204. Up to this we have to, yeah. So up to 297 296, it gives me an answer which is very big, right? Now if I increase another one, it exited with an error. Okay, now let's just create another duplicate tab and use the for loop implementation. Factorial loop. Let's just go with where the recursion is also working. 196 796. Codes are, oh, let's just print it also. Print. Yes. Okay, it prints the same value, right? Now go with some 196 797 where the recursion is breaking. So it's actually getting exiting out of the whole recursion, right? Now for this, if I run for the loop implementation, see, it gives me a result. It doesn't break. Now why is so? It can even compute factor of 1000. See, this is the result. But you can never get this implementation working on 1000. See, it exits with an error. Now why that happens? That's a question, right? So the thing is that, see, this is how these calls are getting made, right? So factor of 5 calls factor of 4, factor of 4 calls factor of 3, factor of 3 calls factor of factorial of 2, factorial of 2 calls factorial of 1, right? So this stack is actually, so each program uh, has a fixed amount of memory that it can access. Okay, so for Python it is very loosely bounded, but for C it is very strictly bounded, that you cannot access more than 300 MB of memory. Okay, if you don't use any, let's say, special libraries. Okay, now what does it mean that the memory allocated to a particular program is always limited. Okay. Now it has two parts. One is heap, another is stack. So this heap and stack you can directly see. Heap and stack. Go to images. So this is what heap and stack means. Okay. So a program has, so the better representation is this. Let's just copy it. I'll add the citations later on, just for your understanding. Stack. Okay. Now a particular memory, a particular program has a fixed amount of memory. Okay. One, like some part of it is reserved for variables, global variables and all that thing, and the rest of the memory being allocated to it is like is actually segregated into two parts. One is heap and another one is stack, and so there is no strict separation among them, so they can grow towards each other. Okay, so if you are not using heap memory, the stack memory can grow, and if you are using heap memory, then the stack memory may reduce. Okay. Now, so this heap. So currently we are not doing anything that like affects heap for now, but this calls, this recursive calls, they actually get stored in stack. So this whole like each function calling its own self is actually stored in the stack memory. Okay, so basically what happens, the the program copies itself and calls itself with this different parameter, right? So for example, what we are doing, we are calling factor of 10, which calls factor of 9. So basically it calls a copy of itself only with a different parameter, right? And then it actually generates a stack called stack. So the previous function copy calls the next function copy, something like this. So now to store these copies, which are known as active records, by the way, right? They store these copies in stack, so they get stored in stack. So stack grows and heap reduces, and it hits a limit when the whole memory gets allocated to the stack. Right, the whole available memory, there is no heap, let's say, the whole memory which was available for these dynamic allocations get filled up, and you get a error, and this is what the error looks like. So in case of C, the error will be more prominent, I guess. It would show you like stack memory exceeded, something like this. Okay, I guess Python also have this error. Python, yeah, memory limit error, yeah. So yeah, you will get a memory error. Okay, and that is what is being happened in this ID, online ID. Okay, but for loop, you see, you are just, it's kind of like an accumulator function, right? The multivariable is getting updated every time, so you are not using any extra memory to compute it. Wherever like the overall computation is same, you are still performing same number of multiplications. You are not reducing the multiplication or reducing this looping also is done, right? This -1 looping, but the looping type is different. So for this range is a iterator, it will add something and multiply, add, multiply, add, multiply. Or here you are doing subtract and then call, that call gets stored in a stack, right? And then it calls the another version which is one less, and the whole stack get cleared when it reaches the base like the base condition or the termination condition. Whenever it reaches 0 or 1, it returns 1, so the whole stack get the upper layer calls are getting basically values from the like its next call. Okay, and the whole stack get like reduced to no, like it gets deallocated and the last value is getting returned here. Like that means 10 times 9 factorial is getting returned at the end. But to successfully compute the whole thing, you have to extend out the stack, right? Extend out all the child calls that would generate, that would take, or that would basically allocate memory in stack. Whereas for loop, it is not the case. It's just updating the previous variable. So there is no memory involved, right? So that's why this this is what I'm saying. These are known as active records. Okay, these are like formally these are known as active records. So because of these active records, recursion is not always the good idea. So you can easily implement some of the logic, let's say this tower of Hanoi and other things with stack, because the problem is set up in such a way that if you think in terms of a recursive call, it would look easier, or it would basically like relate to our thought process, right? But in case if you are implementing it with a loop, it will be much harder to implement. But still, stack is up to 796, right? Up to here we can compute the value. Yeah, up to here. Oh no, 795, I guess. Yeah, right. So up to 795 we can compute the value. So that means for this program, if I am copying only this factorial function, then I can have 795 copies of it in memory. Let's say you have some like a bit bigger function, then it will be able to call less function calls. Okay. So for example, let's just add some garbage, like any something that doesn't change the code, or basically print. We are just increasing the function size. Okay. This is how we are increasing the function size. Now if I run, oh, it still exists. It's still uh, is wait. We can just add all of them here also. See, now for the same call 795, it hits an error because the function size increases. Right now,
Hello.
you will be able to all lesser function calls. So let's say 790. Let's see whether that gets computed or
Hello.
not. Yes, I can hear you.
This compiler prints each iteration.
Uh, what? Can you repeat? I didn't get your point.
This
Hello.
compiler prints each iteration.
Yeah, here I am printing it, right? I am actually printing it. See, printf this. It doesn't automatically print it. I am printing it. Okay. And by adding all this code, what I am doing, I am actually increasing the effective size of the function, right? Whichever it is copying for the active records. So now what happens earlier when this all this garbage code, so this code means nothing, right? It doesn't add any value to the computer, so it's just garbage code, right? But still it increases the function size. So that basically proves our point that recursion copies the function and store it in active records. So now you see you cannot even compute 790. I have to reduce it further. Let's see whether 780 runs or not. Yeah, it still exits with an error. So let's go with 600. Nah, still exits with an error. 500, 400. Yeah, for 400 it is computing. Fine, right? So let's just get to Wait. What happened? Oh, you see, so I was actually creating that new tab that because of this. So that tab crashed actually. Oh no, it's here. Fine. Okay. Now for 500, it exits at 375. At max, you can call for 500 minus 375. So after 375 calls, it failed. I guess it's actually accumulating the memory as well. If I just refresh, yeah, I will be able to. I just refresh the page. Not see. Oh, still exits with an error. So, but if I just remove this all of this garbage code from here and from here, you guys can see me, right? Actually, something. Increase the recursion meter. Okay. Now if I run 500, you see it can return me the value. So that what does this means? It actually copies the function multiple times in memory, right? And let's say as the more bigger the function you have, less recursive calls you can make, right? So yeah, but for loop, that there is no limitation. You can like loop until any number that is like let's say permissible in your machine, right? Or in the language. So you can go with the maximum value of whichever variable is possible in Python, and then you can get its factorial. If it is if the variable if the output can be stored in memory, okay. But for recursion, you have a limit, and that's the limit. Okay, is the yeah. So this is why recursion is not always a good idea. So for example, this graph algorithms, right? I'm not sure whether you guys have read graph algorithms yet. So basically, let's say cities, right? Cities and uh, routes. So you have multiple cities. So if you have board a plane before, right? From top, how it looks like a graph, right? So each junction is actually a node, and all the lanes are basically connecting in each junctions, right? That is called a that's a typical representation of a graph. So just the road network, that's a graph, and each junction point is basically a node, right? So to traverse this type of data structure, sometimes this recursive implementation is done. Okay, but then also there is a limitation that you cannot traverse a graph uh, with this many depth. So the graph should be limited. So you can only traverse a graph with a recursive traversal rule if the graph has a maximum size of, let's say, 300, something like this. 300 nodes. You cannot parse a graph beyond 300 nodes. But for loop, if you are using a looping implementation of the same, then you can parse even bigger graphs. Or actually, like any graph that you can store in memory, you can parse with loop. Okay. Because the implementation doesn't incur extra memory use, whereas the recursion incur make more memory. It allocates more memory in the system, right? You get this point, right? So if you have any confusion at this point, you can just say. So then I will go for some practice questions with recursion. Okay, and we will also figure out where the breaks. So at which point we cannot use that function. Yeah, so this Python also has this recursion limit. See, why I chose a online compiler is because I don't want to change this limit. So this online compiler doesn't give me any access to where to basically change the recursion limit, right? But for my system, I can always use this sys package, right, and then change the set the recursion limit. So that what does it mean? It basically allocates more amount of heap and stack memory. That is what actually is being meant by this call. That okay, allow up till 1500 recursive calls, and whichever memory is needed for that, you just allocate it. Okay. But for this online compiler, you see, we don't have any access to the changing those type of things, right? And let's say this is important for your competitive programming test as well, right? So for, let's say for your system, you can always change the recursion limit, right? And you can implement, let's say you can traverse a bigger graph, or you can get factor of a bigger number. But whenever you are doing a competitive programming test, then in their platform you don't have access to this recursion limit, right? And they basically set it very low. It's not even 100. Okay, so in that case, if you solve a problem with a recursive logic, that would get like resource exhausted error. And that basically many of the students who appear for competitive programming exams, or let's say test, this general hiring companies does, right? Let's say TCS, Wipro, all of them takes tests, this NQT and all. If you implement their problem in a recursive logic, then there is a high chance that your program will fail whenever there will be like basically tested against test cases. Okay, so if they have not specifically said that you have to implement the program with a recursive logic, it is always better to go with a loop. Okay, you get it? Get my point, right? Okay, now let's do some practice problems and see how much we can compute. So what is the limit of that computation, of doing that in recursion? Sum of n numbers. So the logic would look like what? N plus n minus 1 plus n minus 2. This is the recursive logic, right? Plus n minus 3 up to 1. So at 1 I will stop. So what I can do, def get sum of n, get sum of n numbers, and what I would return n plus get sum of n minus 1. And the base case, now I have to also mention the base case. If this n is equal to 1, right, just return 1. So sum of 1 is 1, right? Sum of only one numbers is 1. So that's why I'm just return 1. Okay, you can always say, actually you can say if n equal to 0, return 0. This is what is the actual base now. So you can also get sum of 0, right? That's also valid here then. Let's see. Get sum of 0. It's give me 0. Sum of 1, it gives me 1. Sum of 2, it should give me 3. Sum of 10, n into n plus. So what is the general logic? N into n plus 1 by 2, right? N into 10 into 11 divided by 2. That's the 55, right? So that's where getting 55. Now similarly for loop implementation, so let's just, so we already proved that these recursive calls have a limit. Okay, now let's just see how much you can compute with this function. print get sum of, let's say 100. 100 would be easy. Yeah, it returns me 5050, right? Let's just do it for 1000. Ah, maximum recursion depth exited with an error, right? Now, so you already know that for that factorial function, which is kind of similar length, it was at 797, right? So let's just try that once. Yeah, it can compute now 798. Oh, it can still compute it because it's similar but little bit smaller. The function is a little bit smaller, so we will be able to make more calls actually. Let's go with 800. Yeah, it can compute 800 to 900. Yeah, can compute 900 to the 950. Oh, 975. Oh, it can compute 975 to 985. Okay, 990, 995. Oh, 98. Yeah. So at 98, let's check for 97 too. It still gets an error. 96. Oh, so up to 996, you can get the sum of n numbers. That is this, and you can cross check it whether it's giving you the right value or not. Just by just by doing 900 times 997 divided by 2. 496506. 496506. Yeah, it's accurate, right? So for a function which is having 1 2 3 lines, it can only compute to 996. Okay. Now you see, so how actually people set your questions in CPs is like this. So for the test cases that were visible in the site default test cases, right? Okay, I just compiled 10 yesterday and I find it difficult. 10 standard and I find it difficult to solve programming assignments in this course because the prerequisites were school level mathematics. So, so what I would suggest you, you just stick with the course. Okay, programming assignments are always difficult for the first comers, right? Whenever you are solving some assignments and you don't know the language properly, right, then it is always difficult. But you will, so what you will get from the course is you get the idea of how programs work. Yeah, you can, so if someone is raising your hand, you can just unmute and speak. Is this code we are adding into n factorial? No, I'm not adding into n factorial. You see, I'm adding n to n minus 1 sum. So basically I'm computing n plus n minus 1 plus n minus 2, something like this. Okay, but
So
anyway,
n minus 1 plus n minus 2 plus n minus 3 will be n factorial now.
no, it's plus, right? Factorial is star. So factorial is
Okay.
n times n minus 1 times n
Okay,
minus,
that's multiply. Okay.
yeah, multipliables.
Okay. Thank you.
Yeah, okay. So so yeah, for this query, that this guy has just completed 10 standards, so it's very good that you enroll in the course. You have a really good interest, I would say. So yeah, so just stick with the course. Even if you are facing difficulty with the assignment, that's fine. Okay, everybody faces difficulty with the assignments at any point of his life. Okay, but what you will gain from the course is you get the programming thought process, right? How people approach a problem with programming. Okay, so you can always get a copy, get a calculator and do multiplication 8 times 9, 9 times 10, 10 times 11 like this, right? But what is fascinating for knowing a programming language for you is you can just throw out all those manual like hurdle shape and then just go with some 3-4 lines of code. It will give you a generalized way of computing sums for anything, right? Any number you want. But you have to still write 3 lines of code, right? So that's how. So the approach you should learn, not directly the assignments. If they're difficult, just solve them, see whether how much grades you get, but like don't shy about that. Okay. Okay. So the main gain is you are already getting the thought process, how people think in terms of programming languages. Okay. Okay, so this is how sums and where the sum breaks for recursion. But if you implemented the same code with loops, right, then you can easily compute 966 sum, right? Fine. Let's go with multiply. So multiply means I want to multiply 2 times 3. How I can compute it in terms of recursion? Okay, so this is a bit odd. This is 2 times 3. We already have operator for this, right? 2 times 3. Why I should go with a recursion, right? But let's just for sake of understanding implement it with a. So see directly the logic comes like this. So you can do 3 times 3, that would represent 2 times 3. Let's say 4 times 3, right? You can represent it as this. So it's a recursive thing. That means I can just remove this and implement it like 2 times 3. 3 times 2 times 3, oh sorry, 3 times 3 times 3 is exactly same as 3 times, oh sorry, it's actually uh, wait, 3 times plus, you are going to do plus here, 3 times 3 plus 3 plus 3. So this is what 4 times 3 means, right? Now what I can just do is do this, right? And this one can be represented like this. Okay, so how I can implement it? So this is a recursive for. So this is a the repeating structure I am having, right? Something which is added to some added to 3, and this something is actually, so 3 plus 3 plus 3 plus 3 is 3 times 3, right? So that basically means we can just replace the whole thing as 3 times 3. Same call, same answer. Now how I can represent it as a recursion? Def multiply A with B. Okay. Now multiply A with B, I am implementing it is a recursion, so I will go with the plus logic. So return.
Spelling of multiply
Mm-hmm.
multiply spelling like
Oh,
it's
PIPLY. Sorry. Multiply, right? So A and B were multiplying. Now that means what? That means we are multiplying A with B. So that means A times B. Okay. So for now, let's just replace them with 4 and 3. Same as the example, 4 and 3. So what I will be doing? 4 times, 3 times multiply of 3 comma 3, right? And when I will break, if this variable, this 4, whichever variable it would be, if this 4 is equal to 1, I will replace them with variable later on. Then that means it is 3. So 1 times 3 means 3. Return 3, right? Now I will replace them with variables. So this is A, and this is B. So this is A, this is this is what? B, A minus 1, B, and then this is also B. You get the implementation. Sorry, this is plus. You see, so the
Hello.
cost will be, yeah, you can say.
So Python actually uses this code to compute the product of two numbers.
No, 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 no. So these multipliers are already implemented in your hardware. So because these operations are very repetitive, right? So you will need a multiplication all the time. It's not like it's a special thing. So these are hardware accelerated. So the logic, multiplication logic, is implemented in the hardware. But we are, so for sake of understanding recursion, we were using recursion as a way of implementing multiplication by using plus. So I'm not using this multiplication operator, right? I am using multiplication. So you already know this, right? That instead of multiplying, what you can do, you can sum repeatedly, right? So I'm using that logic to replace this multiplication operator with plus operator. By the way, this multiplication operator is already implemented in terms of a hardware support. Okay. Okay, so just you can just say ki take these two resistors and multiply them. The accumulator will itself figure it out how to multiply it. Okay, so there are multiplier divider circuits you can design. Okay, but so those are actually implemented in terms of silicon, in terms of your draw processing power. But what we are doing, we are not using that functionality. We are implementing it using recursion because we want to test the limit where recursion fails. Okay, so here, so it's the so basically this multiply function represents this hardware call. So to multiply a times b, I am just using the hardware implementation by a times b, and I am using a software implementation which is using plus or addition to simulate multiply using a recursive call. It's basically simulating. So what it is doing is, uh, let's say 4 times 3, so it's actually computing 4, sorry, 3 plus 3 plus 3 plus 3. It's not using this call, this star multiplication operator. Okay, now here we will see where the, like, let's say we are multiplying 3. Okay, I will see up to which number I can multiply 3 with, maximum number where. So because this maximum number is getting, this a is getting minus 1 minus 1 minus 1, right? B is, we are not actually changing b is actually a fixed thing. Now we are changing a, that actually changes how many times the function will copy itself for the record, like the active, like this in his active records, right? So we'll see up to which maximum number we can multiply 3 with by this implementation. Let's just copy it. Is this as a, yeah, multiply, this 3 is fixed. Now I want to multiply 3 with 100. It should return me 300. Oh, sorry, print, I have to also print it. Yeah, 300 as expected. Now let's say I want to multiply it with 200. Okay, 500, still okay. 600, still okay. 700, okay. 900, still is fine. 1000, yeah, it breaks, right? So it breaks as 994. So 994 I can multiply it with, yeah, 995. Let's see. Okay, 996, 97, 28 and it breaks. You get my point, right? So but this computation, if you are using a loop implementation for multiplication, same logic, plus plus, repeated plus. If I am doing a loop implementation that doesn't take more amount of memory, it can easily compute it. Okay. But the loop implementation I'm talking about is like this: for I in range B, multiply is equal to multiply plus A. Okay, and the multiply is basically multiply is equal to 0 at the beginning. And if I just do A to be 998 and B to be 3, I can easily have answer for multiply. Yeah, this is the answer. And I can just cross check it with A times B. Same. So this is using hardware, like raw hardware performance you have, because it's directly implemented in terms of your hardware logic. This is you can do implement a multiply logic with summation repeated sums, right? And you can also use a recursive logic, and they all have limitations. So what does it what does this limits you to, right? Because this star operator is already there, right? It can use the accumulator or your CPU more efficiently instead of like using this creating a separate variable, doing an accumulation time again like this. Okay, so actually this is not efficient. This is the maximum efficiency you will get for multiplication is by using the default operator. Okay, this is not efficient, but you can compute anything, right? But whereas this recursive call, it's basically it fails at 1000. Okay. Okay. Now power. How we can implement power? Power is, you already have a operator for this. Power is star star operator, if you remember, right? 2 to the power 2, sorry, 3 to the power 2 means 9. This is how you implement power in Python, star star operator, right? In many of the programming languages, this is this caret symbol. Yeah. Is somebody saying something? Okay. So power is same, so you can easily implement it, I guess. So power means what? 3 times 3 to the power 3. What does this mean? Or 3 to the power 4. What does that mean? 3 times 3 to the power 3. Right? Same 81. For this also it will get print. It will print as 81. So this is a really simple call, right? This something like n times um, power of n minus 1 comma n. This is what power means, and you are computing it for n to the power n. So I'm just not implementing it. I guess by the time, like by this time you have like pretty good idea how to implement it. It's just the same call with, and the base condition I'm just writing. If you want to try on your own, you can do it. Base condition is what? N to the power 1 means, or n to the power 0 means what? 1. Or you can also close it as n to the power 1 is equal to n. But then the function doesn't work for if somebody passes like this, the power n0, then it fails, right? Because there is uh, no condition to handle this. So better to have the base function like this. Then you can also respond to this call, this power of n comma 0. Okay, guys, now we'll be switching to classes. So this is the so at so till now, what you know loops, you know control flow, like this break continue statements. You already have seen functions, dictionary, and other data types. You know like two types of functions: generators and the generic function that you already have. No recursion. Now it's a good time to start with classes. That's
Hello.
a, yeah,
Is recursion like a while loop?
recursion.
Like a while loop.
Uh, Something like that. So while loop actually doesn't allocate memory, but recursion what it does from this figure, I guess you can better understand it. It allocates memory, and it's allocating memory in the this stack. So a program has a fixed amount of memory, okay, to execute. Let's say a program has or let's 300 megabytes of memory. Okay, so you can allocate memory up to 300 megabytes. Now, if you are allocating memory like in that whole space, so you have a limit, right? 300 memory. So based on the function size, this function copy how much space it takes, you are limited to how much call you can make, for the how much recursive call you can make. But for while loop, it doesn't allocate any memory. Same logic, it doesn't allocate any memory, but it just iterates, right? It just iterates over the, let's say, any statement. So for that case, no amount of memory is allocated. Okay, but the same thing what you can do with a while loop, you can do it with recursion. Okay. So basically, recursion is a clever way of looping, but it has limitation. It has, because it allocates memory, it has limitation in terms of how much calls you can, how much loop you can make. Okay. Now let's start with classes. So what are classes?
Hello.
Yeah, go ahead.
How while loop is built in Python?
So build in Python, see Python is written in C, okay, and C already has this. Oh, wait, let me give you a more appropriate answer for this. See, if you just search and see assembly language, right? See, this is what assembly language looks like. So, and this is what actually runs in your hardware, runs in your CPU. Okay. So now there is a function, or there is a statement actually known as called as jump. For this jump statement is there. Wait, assembly language jump images. Just go to images. Jump. Yeah, yeah. See these jump statements, right? And what it does, it it checks some, let's say, some condition. If it matches, then it will jump to some statement. Okay, that is how if statement, while statement, everything is implemented. This basically, whenever your compiler is comparing it to hardware level code or this assembly code, it's actually representing the whole code in terms of jumps and all, jumps and checks. See this, and I guess you. So I don't know whether you have passion for engineering or not, but if you go for engineering later on, there is a separate electronics course for this. So usually this assembly level programming are considered as a part of electronics course. So for my BTech, I did it on electronics. Uh, this assembly programming and all, everything was like part of the electronics departments. There we have to actually program a 8085 micro controller, right, which works on these jump statements. So if I am trying to loop a statement, I have to do a check, and if the check passes, I have to jump to another, like the above line, and that these line numbers have IDs. So let's say I want to jump to 206 line, so I will just say jump 206. So the program will jump to 206 line. So now based on the check, you can do a loop, right? So this is how, in terms of assembly or any language, C, C++, Java, everything, they gets compiled to assembly. Okay, and then this assembly gets compiled to hardware level language by the, like, let's say hardware specific compilers. So for like for Intel CPUs, the compilers are different because the instruction set is different. This jump maybe jump is represented as JNC for Intel. Let's say for Apple, this Mac M1 chip, it is represented as JMP, right? So those mappings are specific to the vendor. So which vendor builds the CPU. Even for, let's say, Intel i5, i7, the instruction sets can be different. Okay. So in which machine you are compiling your code, based on that, that assembly level code gets compiled to byte level code, and that runs basically on your PC in your CPU. So loops, if loop, everything, these statements are actually implemented with jump and checks. So you can check something is 1 or 0, and then you can jump according to it to a particular statement line. Okay, it's clear, right? How loop and if statement, everything is implemented.
Yes, sir.
Okay. Now classes. So I keep it blank because I want to add the code here. Okay, and later on I will be adding some so if you just come back to this slide later on, you will get some pictorial representation of what classes actually means. So let's just represent it with a box now. Okay, now what class means is, let's say for Python you have these data types, right? This list, dictionary, tuple, all those things. They somehow capture the data, right? They somehow store the data in memory. How they store, what they store, we care about. How they store, we don't care, right? We don't care how they are storing, let's say, a string inside of a integers list. We don't care about that, right? What we care about, that I can get the data out, I can add some data, I can remove some data, I can find some data. That is what we are concerned about, right? So we are concerned about the use cases, not how it is storing the data or how it is internally managing the data, right? So these lists, all this type of complex structures, abstract data types, all they are all actually classes. So this, so for Python, everything is a class. Everything, every object, everything that you can think about in Python, they are all classes. Even this type of function actually returns the class name. Okay, it returns object type, or it basically returns the class name of the object. Okay, so see, already it says key, see, it's all classes. Okay, now type of int is, sorry, type of 2 is an int. This is also a class in Python. So anything you can think of in Python is a class. Okay, for example, list L, 1 2 3, type of L, it's a list, and list is a class. Okay, and why I am saying list is a class, because see, if I do L dot and then tab, these are all the methods that I can apply. Okay, and if I do underscore, these are all the hidden methods that I can apply on this. So somehow it is storing the data and giving me access to manipulate it. That is the like standard definition of what is a class. So just to write it here, class stores the data. somehow I don't care, somehow. Okay, and so somehow, and another thing that classes does, gives me access to the data. So yeah, these two things classes provide us, and these are actually like technical terms to it as well. This is called member variables, and this is called member methods. Okay, so whatever you are storing in the class is called as members. Okay, so this is member variable which I can change according to my requirement, and whatever method I am applying, those are called member methods. Okay, now in terms of list, what is the member variable? These are all member methods. These are all the methods that it exports to the user. You can use these things to manipulate my variables. Now what are the variables that it has? So if I just write dir, you see these are all the things that it implements. Okay, all the things. So now here, let's see where it stores the memory, right? Iterator. So this iterator, this variable I guess would be, oh, it's a function, it's a still a wrapper. So whichever is not a function, add class get item, class dot get item is function. Doc here doc eq means equal. I'll tell all the functions later on. These functions we have to implement for our classes as well. So let's say that why I'm saying it's important to know classes, because you can implement your own data structure. So you don't have to be bounded with these dictionaries, tuples, everything. You can create a custom data structure for yourself. So for your use case, if you need a new data structure that is not there in the Python language, you can implement it. And we will, like, for today we will also implement a data structure that is not there in Python language. Okay, by knowing like how to implement a data structure, you will be able to get all the concepts how classes work. Okay, so these are all the functions and variables that this class L or the list class exports, right? And it's actually different for dictionaries. See, for dictionaries the methods and functions are different, right? Some methods are common. Let's say this LE, LEN, LT, MEL. These methods are common. You see, you can find them here as well. Some of them here, this LEN, LE, LT, all those things. But many of them are separate. Right? There is a disjoint set as well. So some of the functions are available here, but however, some other functions are only available for the dictionary. Right now, so you can actually what classes let you do, define own data type. You can define your own data type. But today, and the instruction looks like this class, and this is a keyword. See, already it is recognized as a bold green. That means it's a keyword. Let me just zoom it in. So now, what class I want to make? Let's say I have a uh, let's say I want to I have two balls, so I have a ball class. Okay, and I have two balls. Okay, So two, let's say a green ball and a red ball. Okay, I want to get the distance between them in terms of let's say Cartesian coordinate. Okay, not polar. So Cartesian coordinate, you already know the formula: x1 minus x2 square plus y1 minus y2 square root over. That is the formula for getting Cartesian distance, right? Now I have to implement a class. Let's say I want to implement a class named ball, um, and I want to have how many things: the location of that ball and the color of that ball, and I also want to compute the distance between let's say ball 1 and ball 2. Okay, now in Python there is no class named ball. If I just try to implement ball 1, see, it's not there, right? So there is nothing then named as ball. So it gets a name error. So that means it doesn't recognize the name. So now I can let Python recognize the name by defining that class, or defining what a ball means. Okay, let's say ball. I want to define a ball. So this is how you define a ball. And by default, if you don't pass anything, okay, let's say you just do pass, you have still defined the ball. Now see, it doesn't get an error. It now knows what ball means. It's a class, something which is a class. And what are the methods that are associated with it? See, these are all the methods. By default, if you just do class and then just do nothing, right? You already have these methods. And surprisingly, this thing also have the same methods. Object. So what does that mean? That means everything that you define is a subclass of object. So subclass, what it means? It's a child parent relationship. So all the, let's say, all the properties of the parent will be copied in the child, right? All the methods, properties, variables there in the child, there in the parent, will be copied as the child in the child. Okay, so by default everything is a object of is a child of object class in Python. So if you don't pass it, it will like assume that it's a child class of object. You pass it, you can pass any, like any class, any parent class like this, ball, and anything, let's say um, rubber ball. You can define a class called rubber ball and then just have a ball class getting the child as a ball class. Okay, so that means, so what does that mean? Let's say let's say I want to have car. Okay, and then under car, Ferrari is a child class. So that means whatever property there will be in car, so Ferrari cannot have 3 wheels, right? It should always have 4 wheels, right? So it basically have the property, car also have 4 wheels. So now you see this is the kind of transitive thing, right? So how many wheels car would have, Ferrari would have the same amount of wheels. So that's a parent child relationship. So that's how in Python everything that is like any property that is there in the object, any class would basically inherit it. Okay, okay, so this is for your understanding. Now how to define a class? So there are two methods. So in class you have to define methods, member and methods. So how you define member? This is what known as the constructor function. Constructor constructor. Constructor means it construct the class. Whenever you are building or using that class, this function gets executed initially. Okay, so if this is a bit confusing, then just let me know. What I will go a bit back and then explain that what classes mean. So constructor means whenever you are first, let's say using that class, this function will be executed at the beginning of that thing. Beginning, at the beginning, this init function would get executed. Now, what is a member? Member is any variable that you define within that int function. Okay. So this dot, or actually not this self, anything that define that you any variable that you define with self dot is actually a class member. So self dot, let's say position. Okay. Now any value I can allocate it. Let's say I allocate it with a tuple 2,3, 1, sorry 1,2. Now it means what? It means like xy position. Okay, position of that ball in xy. Now I never have to define it here. I can define it from the constructor itself. So I can define it here. USI here position, and I can just pass that position, or let's just name it as ball, just to avoid confusion. And whenever I will be passing position, it will be allocated with its member variable. It will be associated with the member variable. Okay, and let's say the color is equal to color, comma color. So this is how you can define an object. Now let's now ball. How I can create a ball? Position I have to pass 1,2. Let's say I pass 1,2, and the color I pass as red. So this is a valid ball object. Okay, and let's just allocate to small or b1 ball 1, and I can access the variables position and color like this ball dot, and see there is no other associated functions. So if I do underscore, then all the functions that are getting copied from that object class or the parent class is there. But if I just consider that only one ball class, right, then in that case I have only two things, this position and color, and those are member variables. These are variables, right? Variables, and these are known as member variables. Okay. Now see, it's printing it's in a gibberish form, right? So that means it's printing that the class is part of main function. This underscore main is representing the main function in Python. Okay, which is the basically the body of the function. And then main dot ball, that means there is a class defined in the main function which is of name ball. So b1 is a type of that. So b1 is a ball type variable which is there in memory location. This is the memory location. So it's represented it's in a hexadecimal form. So at memory this you get a ball object which has these two values associated with it. And how it is storing the value? There is another variable called position inside it, right? And then another variable called color inside it. This is how they are storing the data. Sorry, not B1. Okay. Just get a screenshot of this.
I have this query.
Mm-hmm.
So whenever we call a function, generally we call it at the end of the program as main and like brackets.
Mm-hmm.
So this is another way of calling a function like underscore main underscore.
No, no. Wait. So you are talking about this, right?
Yes, yes.
But so it's actually, like, see, for list 1 2 3 1 to 4 L, if you just print L, you get 1 2 3, right? This representation. But for
Yes.
B, if I print B, it gives me this. So it actually means that in the main function, so this is underscore underscore main is the main function of Python, which is the entire function, entire program. Okay. Then it means that there is a class name ball, and B1 is a instance of it. Instance means you can create another ball. Okay, you can create B2, just like you can create two lists. You can create another ball with different uh, values. Let's say blue. Now B1 is same, and that you have also have B2. So B2.
So here also like in it when in the previous program when you are defining the class, there in defining init underscore underscore like so what is this underscore representing?
So this is hidden. So underscore means hidden. So I can. So you see, you can access that function by doing underscore underscore I. See, this function is there. But if you just, so classes have functions and variables. So this is a special function named as constructor, which defines all the, or which is basically called at the beginning of creating a function, creating an object. So whenever this ball is created, right? This you see. Let's just comment this one and just print
So
something.
this init function this is some inbuilt function in Python, you are not creating it, is it?
Yeah. So this function is already, the name of the function is already fixed. So the constructor is
In
named as
Python.
underscore
In
underscore
Python.
in Python. For C it is different. For C it is the same as the class name. So it's not C, C++. So for, let's say, C++, if you are defining a class and the class name is ball, then the constructor name is also ball.
Okay.
But for Python, it is defined as underscore underscore init. That means at initialization, this function will be called. So let's say initialize, N-I-A-I-L-I-Z-E, right? I just
This
add a print statement
function
here.
this
Now,
function is being called within this class.
yeah. So whenever we are instantiating something, B1, let's say I'm creating a ball B1, just like I create a dictionary, right? I can create a
Yeah.
dictionary like this, DICT, uh, A equal to 1, comma B equal to 2. Now this is the class name.
Okay.
By default, what we do, we do like this, right? 1 colon 2,
Yes, yes.
but we can also call that dictionary like this. So this is the class name, and this is how you pass the parameters. So here these are the
Okay.
parameters.
So if we are not giving curly brackets, then it becomes a class.
No, curly bracket is also a class. This is also a class. This is just like different way of, because it's a like what you can say. It's already integrated in Python, so you can just use these curly braces to. So these two things mean the same thing. Similarly, you can use a list with third bracket, right? You can also use a list like this. Oh, sorry. Uh, you have to pass iterator, same, just like this. So it's a iterator, so you can also pass it tuple if you want. It takes an iterator as an input. Whatever range also would work. Let's say range 10. It will create a range of 10.
Okay.
So you can use this third bracket notation, which is, that is because Python lets you use that third bracket notation because it is integrated in Python, right? Just like
Yes.
in dictionary, you can use the curly notation, but the without using that, you can directly use the class name as well. The dictionary is a class name, that you can directly call and instantiate a dictionary.
Okay.
Similarly,
And
because ball is not there in Python, right? We defined it. That's why
yeah.
we have to also initialize, define how it will be initialized. So this is the
Okay.
initialization function. So let's just call it once. See this
So
initialize.
every class will have a initialization first.
Yeah, yeah. This is how functions are initialized. Now, now how the see how if I am printing B, it's printing like this. But similarly, for list L, it is printing a list. It should print something like this, right? Underscore underscore main dot list at the date at some memory location. But
Yeah.
it prints the value. So how it is doing that? So there is a function that you can define with that class, which will be executed whenever you are printing that object. For example, I can have def. The function name is little bit peculiar. REPR representation. This function will be called whenever you are trying to get the representation of the function. So by default, it returns this underscore underscore main at the rate memory. Okay, if you define it, you can define it like this: print. Let's say I define it like a uh, call and colon uh, self. So to get the variable from here, I just have to write self dot. Self mean class variable. Okay, so whichever you have defined it in the constructor, self dot position, and this just because it's a yeah, it's already a tuple, so it will be printed in a first bracket, and then color colon.
So what is this F before the ball?
Oh, this is string formatting. I'm using this representation, string format representation. Sorry.
String is by default. Huh?
No, no. You have to write this app. Otherwise, you cannot use this type of the curly braces to the color, right? Yeah. So to make this a
Hello.
valid, yeah. Go ahead.
Uh,
So main is an inbuilt function
Yeah.
in
Yeah.
Python.
Yeah. This is underscore underscore main.
So this we are not creating. If in
No.
our program we create, if we define a function named main,
No.
then
So see, it's not a main function. It's actually main scope. So you can check if you are running in the main scope. Main is it so
you said main is what it is a.
main scope. It's a scope. So you are running under main function scope. So this is not a function. This is a scope. In that scope, there is a ball class, and you have an instance of ball B2, which is allocated in memory. This in memory address this.
Okay.
Hello.
Yeah, go ahead.
Hello.
Yeah, I can hear you.
What if
What is?
we use the same member variables like that of the list, that l dot append l
Yeah,
something,
yeah. We can
we
initialize.
create
So
with
actually, so
same
actually,
variables like
it's the
l
same
dot
thing.
append self dot position, no, like that l dot append.
Yeah, yeah. So similarly, what L dot append does, you can also allocate a like also define a function that does something with ball, the L ball dot throw, something like this. So all the gaming, let's say game engines and all, right, they defined objects like this. There is a ball object, and there are methods associated with it. So whenever you will kick the ball, let's say click on the ball, right? Then let's say kick method would run. No, now the ball would get let's say the, it basically moves, right? So the and in the kick method, the move logic is there. So how the ball would move? Okay.
No, if we find the same like L dot append, then it will create a confusion. No,
No, no, no. So you are saying ki I am, if I define a function same as the, let's say if I am,
self with ln, that way.
where where you are saying just,
No, like self. No, if we defined L dot append, same
right?
class, and
Uh-huh.
we write a program, then it will create confusion. No, when we again use L dot append.
No, no,
Uh,
no. So so it's actually replacing the previous one. So whenever you will be redefining a function, it will replace the previous one. So if you define two functions, right? Let's say I define two init functions here. Position, I am in the second one, I am not using this. See, it expects only position. Now this earlier function, it actually replaced by the new one, whichever is at the bottom. So if I, let's say, define another function and I just replace, I have no parameters now in the init. Now you see, it doesn't expect any parameter. If I try to give any parameter, it will show key, okay, it only takes no parameters. It takes no parameter. You have given three parameters. Three parameters is because this self is considered as a parameter. Okay. So see, for this class and everything, we are just introducing to you this concepts. Okay, so there will be lot of like I guess 2-3 weeks will be gone by like, defining what class does and doing practice questions. Okay, it will take a lot of time. So class is a very vast topic. So for now, you just see, just take it simply. You can define your own data structure and how you can define the members and function. That is the goal currently. Now it will, whether it will replace or whether it will get confusing for if I define two sim functions and all that thing, like that, those things will come later on. Okay, now like we already know that Python doesn't support overloading. It cannot have functions that are having the same name. But for C, you can have functions that have the same name but different parameter list. That is called overloading, right? But for Python, if the name is same, the function would get overridden. So the previous function will be replaced by the new function. Okay, that's why see in this implementation we have three init functions, but only the last one is effective. It expects no parameters, right? It expects no parameters. But if I just remove it, right, and run, see, it expects only one parameter, position, POS. Now if I remove this one too, now run, now it expects position and color. Get it, right?
yes.
Okay, so we'll see how we can. Uh, so what we are talking about earlier was why printing B gives me this underscore main ball at the rate location this, whereas list is similarly an object, but it gives me the values. How it is giving me that? So to implement this feature, when I am trying to print that function or get the or try to see that variable, or try to see that object, give me the actual value of it or some representation of the value, I can use this special function repr underscore repr, which means representation. That's it, representation. So this I underscore init, this means initialize. This repr, this means representation. Okay, so what I am representing the ball with, let's say the representation is this: ball colon its position comma color, and let's just have a third bracket, or let's just have a um, what I can have. Let's just have dollar. So the representation is dollar ball colon position comma color colon color dollar. This is my custom position, the custom representation that I have came up with. or ball. Okay. Now if I run this, I created a ball B1. If I try to print or try to see the ball B1, it gives me that representation. Ball 1 comma 2, because I passed 1 comma 2 comma red. If I see B2, if I just B2 is blue 2 comma 3, both of them are initialized, and I try to see B2, it gives me it's a ball, it's 2 comma 3 and its color is blue. Now you can connect, right, how this dictionary is getting printed, how this list is getting printed. Wherever you if you just uncomment it, comment it, you see now ball is something random, this main ball at the date some memory location. But if I just uncomment it, I can now have my custom representation of the data. So that is how this list and dictionaries all they are implemented. So in their representation function, they are representing it like this. Let's say I wanted this type representation. I would say I kind of do like this. Print the position, print the color. Okay. Now see ball print as a third bracket, then the pair of position comma red. Ball to same. So now you can connect, right, how these dictionaries and list are also getting printed like this instead of something dictionary at memory this. So if that function is not implemented, let's say your dictionary would print like this, underscore main underscore dot dic at 0x12 something, some memory location, and then end it. This is how it should print if that this representation function is not implemented for dictionary. And we can see actually, so we can also modify the representation function. Okay, see how we can modify it. Now this becomes interesting. Now I can modify the behavior of a dictionary according to my need. So let's say I want to modify the print statement or how the dictionary is getting printed. Currently it is printed like this, right? Third bracket, the key colon value. Now let's say I want to print, let's say dictionary is there. So let's say I want to print this dictionary like this, a equal to a comma b colon 1 comma 2. Wait. Okay. Now see. Now let's say I want to print dictionary 1 comma 2 like this. How I can do that? Because now you know that print logic is implemented in this function. I can have a dictionary. I have my dictionary, right? Class my dictionary, which inherits everything from the dictionary, and I don't change the init function. It is same as the default whichever is there in the default. I just change the representation. Okay. Representation self, and to connect it to dictionary I have to define the init here. Init self. So I will explain everything what I am doing here now later on.
So self is taking dictionary here.
Uh-huh.
Self is taking dictionary function here.
What you are saying, I cannot understand it.
I'm
Can,
saying self is taking the dictionary function here. Self.
which one? Are you saying something in chat? Oh, self, right? Yeah. wait, this is dictionary. So it's actually saying you inherit or you copy everything from dictionary. Okay. Okay, or let's just go with a simpler implementation. Wait, I get your point, what you are saying. So let's just go with the simpler implementation and later on discuss how to extend a class. Now self comma data is equal to data, or let's say dictionary that I will pass from here. Okay, and the representation what I can do, return the implementation I want here, right? So I want string into here self dot data dot keys, all the keys I want together and I want them as tuple. You just format it. So all the keys will be represented as a tuple, comma, all the values will be represented as a tuple, like same representation that I want for my dictionary, right? Yeah. Now let's try my dictionary. I have a colon 2, sorry, a colon comma b colon 2 c. Oh, sorry, no, change it to values. See, now I have the representation I want for my dictionary. It's not uh, same. And let's say if I want the same representation, I just represent string of data. Whatever they are in the implementation for the dictionary, it will be written. But if I want a different representation, when I am printing it, it's not actually affecting how I am storing the data. I am still storing the data in a dictionary, but whenever I am printing it, it is getting represented as I want it. You get it, right? What representation function means and what init function means. Print. This is initialization, and this is where representation means print representation. So if I just see, both of them get executed. Why? Because when I am only like just creating it, not allocating to let's say some variable a, both of the function get calls, right? One for initializing the dictionary, second is for printing this out here. This representation function is also called. But if I just allocate to a, see, only initialize function gets called, and whenever I am seeing a, right, whenever I try to see a, then that representation function is called. Even if let's say I want to print a, that representation function is still called. Okay. Any doubts till now?
So this is object-oriented programming.
Yeah. So for until now you have all the knowledge of how to make procedure, right? This procedure-oriented programming was ended at recursion. Now it is how you can use those procedures and make objects. Let's say the objects you can understand it how game works, right? So if you kick a ball, it would work differently if you kick a, let's say, cat, right? If you kick a let's say dog, then it, or anything in a game, right? If you let's say if let's say you are playing a car game, right? Then in that case the car would, like, different cars would move differently, right? All those are represented as classes. So let's say a motorcycle we represent it as a motorcycle class, a four-wheeler we represent it as a, let's say, a car class, right? So now procedure oriented programming, there is some logics are there that you can easily deploy, easily implement in terms of objects. So for that, it's very important to know how object oriented programming works. And Python is anything that you will be using Python for, let's say for machine learning, for analytics, anything, object oriented programming will be a big part of it, like a very big, very big part of it. Okay, because everything, these neural networks, these are also objects. Okay, these neural networks, this, let's say anything, these data sets you are using, right, they are also objects, basically big dictionaries, big like usually data sets are represented as dictionaries or arrays, but they are also objects. Okay, objects in a memory, you can apply method, get data out of it, like put data into it. So you have to know how to, like how this you already know, you like until now, if you don't know this concept of objects, I bet you have think the dictionaries or list, these are not objects, these are data types, right? Data types that Python exports, but they are also implemented as a object. Everything, this integer, float, these are also like implemented as objects in Python. So now you have the, like now you are kind of getting deeper into Python, that okay, now I want to change the behavior of a list and to change the behavior of a dictionary, right? I change the behavior of the set I am using for my work. Let's say set doesn't have order, right? Set is an unordered list, so you cannot order a set. But let's say I have some application, okay, I have some code to work, like I have some code to do where I need a set that is ordered. Okay, so in that case I have to modify the behavior of the set. Those capabilities will be only available if you can change the object behavior. So those things we will learn now. Okay, these are kind of the stuffs that you can only use to modify some object, or let's say create your own objects, create your own data types and all. Someone is writing something.
So we will have another session for this na next week
Yeah, yeah.
for class and everything.
Yeah, so this is basically the introduction session, right? This is just the introduction, or what basically class means. Later on, we'll, like there are a lot of theory behind classes too, a lot of theory and lot of applications too. So I guess we'll have 2 more weeks on only class and how to use them efficiently in your implementation. So anything you are doing, right? Let's say you are handling a coordinate system. No. This course is like not meant for higher class. So classes are like by default it comes under overall Python thing. Okay, so you can use them for a lot of interesting like implementations. Okay, so you can just touch them, like touch upon them, and then we'll move for the like remaining material of the course. Like just for the inclusivity of the course, right? If you don't learn class, then you miss a lot, like miss a huge part of Python. So I guess this like eligibility you already told, right? It's for 10th class students, 10 plus mathematics. Okay, anyway, see, we'll uh, we'll touch upon class a bit because it will get you more understanding on how to use those list objects and all those things, right? List, dictionaries and all. So if I, let's say, want to change some behavior of it, you can like after knowing class a bit, you can do that, and we'll show you some use cases like this. This is where you need a like this behavior in a dictionary. Let's say I want sorting behavior there, so I can use a class that sorts the keys. So even if I insert a key, let's say I insert a key at random position, I insert 2 first and then 3 then 5, but the class is defined in such a way that it automatically organize the organize the data in a ascending or descending order. Okay, this type of behavior you can introduce in a by using classes. But anyway, so classes I will keep it as a optional, so we'll just touch upon it, not deeply, but just overall. Can you modify the Can you modify the range function? But like, why do you need to modify the range function? Like, how would you modify it? But you have to know, okay, how would I modify the range function, right? But anyway, so classes are they, like, we will only see classes how to modify the behavior of a data, but rather than like, other than that, we'll mostly stick to the okay, okay. See, so for that you don't need a class actually. That's it. That's just another wrapper. Range. See, it's a function. It's not a class. Okay. So type. So it's a iterator. So iterator class. Wait. It's an iterator class. Range. Okay. Now see what are the objects that I like, what are the properties that I can have. Range dot. See this count, index, start, stop. Okay. Now step is also there. So now let's see, start 0, stop 10, right? Count is a some function. Okay. Now what it takes, it takes a value, returns the occurrence of that value. Count is count. Let's say if I want to count 9, it is only one time present, right? Now what are the other functions that are there? Index of 5, 4 is 4, that's also fine. Now let's say I want to have, let's see whether I can do it. My range, and don't see the code for now. Stop, start, stop, comma, step. Here I pass step. No, sorry. Oh, range is not an acceptable base type. So, um, sorry. We can just have this. You can represent it as like this, self dot range is equal to range like this. Let's say I want a range, my range, okay, uh, and call, yeah, something like this. Now my range would be 0 to, let's say, 10, and I don't pass anything, just let's say pass everything, 0 to 10, 0 to 10 comma 1 step. Now this is a range function, right? In the representation I can just print return self dot range. Sorry, it's already to screen. Yeah, see, even if I am passing it 10, it's showing as range 0 comma 11. Okay. Now to get this, to get the next function, there is this function next. object.
So
So
we are calling a class also in a similar way, like we call a function, and we give the parameters also the same way like the function.
yeah, but the data is there, so I can save it actually. I can save it and I can modify the
Okay.
data. So I can modify my range to be something else. You see? So so what is the difference between a
Okay.
class and a function? So function doesn't have any memory associated with it. Whenever you call it, it just get called and operate on some operators, operate on some operands and give you the result, right? But for classes, you can associate data with it. So you can also save a data
Okay.
and a function. I mean, it's just like combine data and a function package kind of thing. Okay, so that
Okay.
means
Thank
it
you.
has memory. So you can modify an object just like let's say there is a bird object. The bird can have color, right? That's a data. That's not a function. But that bird can have a fly function, right? So these type of concepts are represented as a class. There is a data associated with a function. So the bird is an object. Let's say color and weight is the data and fly is the function. So that whole thing is represented as an object. Okay. Okay. Anyway,
Yes. Thank
I
you.
yeah. Okay. So I think it's a bit confusing for you now. I'll try to explain it a bit more with pictures and diagrams in the later classes. Okay. And kind of connect you with actual use cases of functions of classes where we can use it, where a functional representation or functional programming logic is bad, and where a function where a let's say a object oriented programming logic is good. Okay, it's mostly how you manage data. So you can manage data more efficiently and data and methods more efficiently with objects if you implement them as an object. But if you implement them as a function, then you have to maintain data separately, maintain functions separately. That would be really hectic for uh, and also the number of lines of code that you have to write would be more in if you go with a functional implementation. But if you just go with a class implementation, you just have to associate a function with a class and the data elements. It will be much easier to handle, much easier to debug the code. I will just have very much like two or three good use cases of it, okay, and then explain you where the functional representation is good, just like this recursion and loop, right? We see where the recursion fails. Similarly, we will see where the functional implementation fails, and this no, I don't think procedure to what is the procedure to approach program. Okay, wait, let me just end this. So we'll see where this functional approach is good and where the object oriented approach is good. Okay, and for that we will just
So,
later on.
this object-oriented approach also has a disadvantage, like the flexibility decreases, like because the class is predefined, so maybe we can't modify much.
No. You can modify anything. So any behavior you want can be modified. So
Okay.
there are
If we,
so there are
we if we are calling a class as such, then it will do the predefined like function only, na, which we have defined.
yeah. And then let's say you if you want to add a new behavior, you just create another associated function with it. Just go there and create a another member function that you want, then that class would be updated.
Okay. Okay. Yeah.
So
Thank you.
yeah. So in terms of functions also, right? If you want a new value to be computed, you have to define that function or change the current implementation. Similarly, if you want new features to be there in a class, you have to just go to the class implementation, add that feature to it. Okay. Okay, we'll just explain it in more details in next class, I guess. And for this question, how to approach the programming assignments, see. So currently, I don't think. So what was the last question? So can anyone just like post which assignment question was there in the last whichever you have submitted, not the current one. Or I have to just go. I'm actually enrolled to the last year.
Yeah, so I faced one issue in assignment question. So
Mhm.
there, what I don't remember the exact question, but I had given the solution using a list. But the recommended solution that I got was using an array. So if we use a list or if we use an array, does like
But
because in the question, yeah,
array and
in the
list are same
question they
file.
were saying you are provided a list. So because they were saying you are provided a list, so I used the list. But then they solved it using an array.
But array and list are same, right, in Python?
Uh, I think they are used differently. Like they were using it
So
differently.
can okay, I'm a bit confused. So see, for Python, if you are not using a package, let's say for NumPy and all, right? Those are packages for numerical computations. Okay, NumPy is for numerical Python. So for those libraries, you have arrays, but in terms of generic Python, you don't have a array data type. You have a list data type which works as an array. So maybe I have to check the assignment. I have to check what is the question. So if anyone remember that, just put that in the chat. I can see. But
Y- I will share the question next time, next week maybe.
okay, okay. So maybe there is something wrong with the implementation. I have to see and verify. Okay,
Yeah, thank you.
okay, okay. So like see you guys next week. So we'll cover classes a bit more in bit more detail and other like course materials also. Okay. But classes are mainly for the next week. Next in the next to next week, we'll again back to the like let's say tuple and everything, how to use them and all those things. Okay, okay, guys, bye bye. Just stop sharing the screen.
Thank you.
Thank you.
Thank you, sir.
Thank you.